So at this point, you're probably very familiar with the concept of an ideal gas. But what we're going to do in this video is I'm going to introduce you to the concept of an ideal solution, which is very different from an ideal gas. And so to do this introduction, what we're going to do is we're going to consider the following system. So we're going to consider that we have a non-reacting mixture. So we're not going to be making bonds, and we're not going to be breaking bonds. So we have a non-reacting mixture that is comprised of 10 moles of some substance A, and then 10 moles of some substance B. Okay? And for substance A and substance B, they're each going to have different molar enthalpies. So substance A is going to have a molar enthalpy of 25 joules per mole, and substance B is going to have a larger value. Its is going to be 75 joules per mole. And since we have 10 moles of substance A and 10 moles of substance B, the mole fractions are going to be equal to one another. They're going to be equal to 0.5. And so for the individual pure components, we know their molar enthalpies. But what we want to figure out now is what is going to be the molar enthalpy of the mixture, that solution that contains both substance A and substance B. Right? Now, based on our intuition, based on problems that we've done, involving steam tables and when we're handling steam quality and things like that, intuitively, you may expect the molar enthalpy of the mixture to just be a weighted average of the pure component molar enthalpies. So you might expect it to be a weighted average of HA and HB. Okay? Alright, and so mathematically that would look like this. So our molar enthalpy of the mixture, and we're going to call this a guess, would just be something like the mole fraction of A times its molar enthalpy plus the mole fraction of B times its molar enthalpy. And if we plug in all these numbers, which we have right here, what we would get is a value of 50 joules per mole. Right? Essentially right between HA and HB, and that makes sense because the mole fractions are going to be equal. Okay? Alright, and so this is just sort of the intuitive answer, or another way to say it is this is a very naive answer. But is this answer the correct one? Right? Is this actually what the molar enthalpy of the mixture is going to be? Okay? Alright, and so in real life, if you wanted to evaluate this, you would do some sort of experiment. Okay? And so, let's do a thought experiment involving 4 different pairs of chemicals. Okay? So our first chemical, 1, 2, 3, 4, 5, 6, is N-hexane. It's just a very simple alkane molecule. Second chemical is N-heptane. So instead of 6 carbons, it has 7. 2, 3, 4, 5, 6. We'll also look at 1-hexanol, which is just like N-hexane, except now it has this extra hydroxyl on the end. The last chemical we'll look at is cyclohexane, which has the same number of carbons as N-hexane, but now the ends have been bonded together. Okay? So we're going to look at these actual chemicals. Instead of substance A and substance B, we're going to look at actual chemicals. And in order to determine the molar enthalpy of the mixture, essentially this is the experiment that one would do. Right? Basically, you would take some sort of vessel that had substance A in it, and you would drop in a drop of B. Okay? All right. And then, as these two things mix, if there's a release of energy or something, that energy would come out as heat. And then based on the energy balance of the system, right, because there's no shaft work going on or anything, and let's say this entire system is in a thermal reservoir, at constant T. So that the change in temperature is also very low. In any case, the heat that's released from the resulting mixture would basically be something like this. Here. Okay? Alright, and so if you can measure the heat and you know what this value is, then you could figure out what that HAB of the mixture is. Okay? Alright, and so that's the basic premise of this experiment. And so we're going to look at 4 different pairings for our mixtures. Okay? For the first pairing, substance A is going to be N-hexane, and substance B is also going to be N-hexane. Right? So we're just adding the same chemical to itself. Right? That's the basic idea. Alright, actually, alright, and so that's would be the first pairing. And so, if one goes out and measures the HAB there, in units of joules per mole, what you would find is that the HAB would also just be equal to 50 joules per mole, right? And that makes sense because you're taking a pure component A and you're just adding in the same chemical back to it, right? So there's going to be no change there. Alright, the next pairing we're going to look at is substance A is going to be N-hexane, and then substance B is going to be that N-heptane. Right? And if you add in drops of N-heptane to N-hexane, by the time you have an equal molar mixture, you would see that the molar enthalpy of the mixture would be slightly higher than 50.46. Right? You would see that a little bit of heat is released from that solution, but not too much. Now, if we change the droplets being added to the system to 1-hexanol, however, you would see that a lot of heat would be released from the system as you added the droplets of the hexanol to the hexane. And in the end, your HAB would be about an order of magnitude larger than it was originally. And the reason for that is because N-hexane is just carbons and hydrogens, but the 1-hexanol has this hydroxyl group on the end. And these hydroxyl groups like to undergo things like hydrogen bonding and stuff like that. And so when that 1-hexanol is pure, those OHs can interact with one another. But when you start adding it to a mixture of N-hexane, a lot of the molecules that's next to don't have those hydroxyls, so you lose the energy of that interaction. Okay, and as a result, that energy has to go somewhere, so it gets released as heat. Okay, and so the reason you see a big difference in the HAB is due to the fact that you have different interactions between the two chemicals. And the last one we're going to look at The last pairing is going to be N-hexane. Oh, this should be B. N-hexane and cyclohexane. Okay. So in this case, cyclohexane is also made up of hydrogens and carbons. But if you did this measurement, you would see that the final HAB would be 266. Okay? So it's not, it's still much larger than the HA of the pure component. And the reason for that is that even though, the cyclohexane is made up of carbons and hydrogens, the molar volume of cyclohexane, because it's its ring, is much different than the molar volume of N-hexane. And so if you start mixing, when the cyclohexane is pure, the molecules are able to arrange in such a way that it helps minimize the energy that each molecule feels. But if you start adding in cyclohexane to N-hexane, these two molecules are, take up different sizes. And so the cyclohexane can't arrange itself as well as it would want to, right? And so due to that reason, due to the fact that the molecules have very different sizes, this leads to a lot of heat being released from the solution, and the final molar enthalpy of the solution being much higher. Okay. All right, and so these are the observations that you would see when you mix these different chemicals together, right? And so in the first case, and even in the N-heptane case, we see that when you mix them together, basically the final molar enthalpy of the system is about the same, okay? And so when we have mixture pairings like that, what we would say is we have an ideal solution. Okay? And so to define an ideal solution is a mixture of molecules with similar sizes and interactions. Right? Basically, if you dropped, put a drop of substance B in substance A, the B molecules in an ideal solution wouldn't be able to tell the difference between themselves and substance A. And so when we talk about an ideal solution, that's what we mean. Okay? I should also mention that ideal solutions, here I kind of framed it as we were putting two liquids together. But the ideal solution concept applies to all phases of matter. So you could extend it to liquids, solids, and even gases as well. Okay? At this point, I should also emphasize that an ideal solution is not the same as an ideal gas. Because remember, with an ideal gas, the inherent assumptions there are that the molecules don't interact with one another, and that the molecules also have no size. They don't take up any space, right? While with an ideal solution, we are specifically talking about how the molecules do take up the same amount of space and that they have interactions with one another. Okay? All right, so an ideal solution, is a sort of framework for understanding how chemicals behave when they're being mixed together. Okay? And mathematically, if we talk about the molar properties of an ideal solution, if we take some property of an ideal solution, so some molar property, so that could be enthalpy, or it could be molar volume, or molar Gibbs energy. basically it would just be, if the solution is an ideal solution, just be the summation of the mole fractions times the molar property of the pure component. Where C here is the number of components or number of different chemicals, number of different species in the mixture.